In part 3, we saw how purifying selection kept our model population herded into the square at the top of the pyramid, seemingly without any ability to evolve further. The introduction of another potential source of fitness, denoted by the purple pyramid, had no effect, because the population did not have the necessary genetic equipment to make use of it. Moreover, our simple SNP-based variation model is unable to deliver any such ability. There are many examples in nature of that kind of entrapment in an evolutionary dead end. However, Orgel's second rule offers an intriguing suggestion. Evolution is cleverer than you are. This means that natural selection, through iterative processes over vast timescales, often produces solutions to biological problems that are more ingenious or effective than those humans might design or anticipate. It underscores the power and creativity of evolutionary processes in generating complex adaptive systems. From our vantage point at the current end of history, and equipped, as we are, with many sophisticated scientific tools, we can look back at past events and investigate some of the clever solutions that evolution by means of natural selection has employed. We can then extend our simple model accordingly. We have been watching purifying selection, preventing the retention of any SNP mutation that results in a landscape position outside the square boundary at the top of the pyramid. But what if, and it's not one of Darwin's big ifs, what if natural selection has exploited another form of genetic variation, one that results in the duplication of one of our two genes, thereby adding a third dimension to our genome model? Subsequent SNP mutations to the X and first Y will continue to be subject to purifying selection, thereby keeping this new strain within the square. However, any SNP mutation to the second Y component will be immune from such attention, and many such variants will appear in the population. If any of those variants result in a fitness advantage, they will be favoured by natural selection and increase in frequency accordingly. In effect, this has added another dimension to the genetic space occupied by the model. That makes it increasingly difficult to visualize if we represent it spatially. So let's use color coding in purple to denote individuals that have this additional genetic dimension and have therefore evolved an ability to make use of the fitness resources denoted by the purple pyramid. Following what we see in nature, we have modelled this capability as an alternative source of fitness rather than an additive one. So, the fitness level along the z-axis doesn't change. The original XY strain can only use the green pyramid, but these new mutants can switch between green and purple when necessary. So, let's introduce some cyclic changes in the fitness landscape and see how the model responds. When the green pyramid is removed, the purple strain climbs to the top of the purple pyramid and the green strain goes extinct. Thereafter, the purple strain can survive on either pyramid, and it can still survive on the edge of extinction if both pyramids are removed. But of course, it doesn't end there. The original green strain has now gone extinct, replaced entirely by the purple strain. But mutation marches on, and the whole process of gene duplication and SNP mutation can be repeated many times. This results in increased difficulty in depicting model performance as seen by our camera drone flying around the fitness landscape. Consequently, an alternative representation is required. Welcome to the primordial alphabet soup kitchen. Remember that Darwin told us that his three preconditions for evolution to occur apply to any being. In the soup kitchen, our beings are simple character strings consisting of letters and a space. We start by seeding the primordial alphabet soup with a single character chosen at random. The character is free to move around the kitchen, and in accord with the three preconditions, it can reproduce identical clones that are subject to mutation. Mutations of the SNP kind simply change a letter to a random alternative, and we can control the rate at which mutations occur. We can also control the speed at which the models move around the kitchen and reproduce. As before, the population size is limited by a relentless fight for survival. Since the letter E has the most frequent rate of occurrence in the English language, we have arranged the fitness landscape in the kitchen to provide that letter with a slight fitness advantage. Consequently, once a letter E appears, it spreads rapidly throughout the population. If we now switch mutations off, purifying selection will remove all other letters and E will become fixed in the population. This happens irrespective of the letter chosen as the seed. As before, we have built in the second form of mutation representing gene duplication. When this is switched on, gene duplication occurs at very low probability, resulting in individuals with two letters, and the second letter can be subject to an SNP mutation without degrading the fitness accrued from the first E. We can now switch to high speed and let the model run for many millions of generations. The wild type display shows the consensus sequence of the evolving population. The length of this string increases as the process of gene duplication and SNP mutation is repeated many times. The evolving wild type string looks like a randomly assembled jumble. But is it? To find out, we can press the reveal button and get the soup kitchen to reverse the order of the letters. In part 5, we will look at what's happening here in great detail to try to determine if it's just a simple deception or a meaningful illustration of the power of evolution by means of natural selection.